of the YouTube streaming because it takes some time. Mhm. Okay, so I think we can start. So, so thank you, everyone. Today we have the pleasure to receive Tiago Mendes Santos from Max Planck. So he's going to talk about machine learning and critical behavior. So Tiago, thank you very much. And it's a great pleasure. And you may start whenever you feel ready, okay?
Okay. All right. Yeah. Thanks for the invitation, Pedro and Lucas and the whole group. I think it's a pleasure for me to meet you guys and to talk about my work. Yeah. So this work. So what I want to talk about today, it's using some concepts and methods from machine learning in many-body physics. Okay, more specifically in phenomenon in systems that are close to a critical point. So basically, the basic idea, let me start with an overview of the basic idea, what I want to show to you. So what we want to do at the end is to do what people do in machine learning is to analyze large data sets. Okay? So here I show some examples, these handwritten data sets, like when you write in your tablet, you produce these data sets. Okay, so basically you want to analyze these data sets to do something, like for example, to do image recognition, for example, to recognize that you wrote a 5 or 1. Okay? So here we more specifically are interested in physical data sets, okay? More specifically in physical data sets that appears in the context of many-body physics. Okay? So here I showed the picture of two pictures that show one is like an image that people measure in experiments with quantum simulators. Okay, so the idea of this quantum simulator is try to emulate a many-body Hamiltonian. Okay? And then they can do this image. So where the bright points means that you have a site with an occupation equal to 1, for example. And the dark points, it's an image sites with occupation 0. But this is really wave function snapshots. If you want. And in the downside, I have like images that I get in simulations, in Monte Carlo simulation. Okay? But at the end, these images are like the data sets, as I show here. Can you see my cursor?
Yes, yeah. Yes, yeah. We can see.
Yeah, so, but at the end, these images are like data sets. So each row here, it's like an image. And then you have a bunch of images, okay? And the idea is like, can we characterize phase of matter and phase transitions more specifically, with these raw data sets? Okay? So this is the basic idea, what I want to do here. Okay? And we do this through this concept of intrinsic dimension, okay, that I mentioned, that is mentioned in the title. So let me give you an idea, like an intuitive idea what this intrinsic dimension is. Okay? So basically, the idea is that real data sets can be seen like as points in a high dimensional space. Okay, so basically, so here in this picture here, I have a data set that has just 3, let's say, particles, 3 coordinates. But the idea is that real data sets, they have a structure. Okay, so basically, in this example here, this Klein bottles data set, the idea is that despite the data set is embedded in a space of 3 dimensions, okay, so we have 3 coordinates, we can lay down this data set in a manifold whose dimension or intrinsic dimension is equal to 2. Okay? So the intrinsic dimension is nothing else but this effective dimension of your data set. Okay? That lives in a high dimensional space, of course. So here is just 3 dimensions, but you see later that when you talk about many-body physics, of course, we have high dimensional space. Okay? So the idea then, what about physical data sets? So then before start giving more overview about the field, let me give you an example in the context of physical data sets. Okay? of the intrinsic dimension in this context. So here, what I will talk about more specifically is about partition function data sets. Okay, so imagine that you have a system at thermal equilibrium, okay, at a temperature T. Okay? And then if you want to describe the system, you need to define, you can define a partition function, right? And then with this partition function, basically, you can compute everything, you can compute thermodynamic quantities. So in the partition function is a sum over the exponential large number of configurations, right? And these configurations, so here we are all the systems that you treat here are discrete symmetries, or systems that are defined in a lattice. Okay? So the idea is that these configurations here are nothing else but points in a high dimensional space. And another important aspect here about the partition function is that most of this configuration has a probability, right? The Boltzmann weight associated to most of this configuration is essentially 0, right? So, of course, this depends on the temperature, but so just few configurations of these high dimensional possibilities has a weight that is like considerably different from 0, right? So let me then show an example of this, okay? So basically here is the simplest example that I will show today is this 3-spin XY model. Okay, so basically you have 3 spins and these spins are described by this Hamiltonian here. Okay, so basically this is the energy of the system, and with this energy you can compute the partition function, right? And here what I did is that I simulate this very simple system and I generate this point. So each point here in this cartoon it's one configuration. Okay, so the configuration here this is defined in this way here. So θ1, θ2, and θ3. Okay. But here you already see something interesting, right? So so if you sample the partition function at a temperature that is super small, okay, so basically the entropy you play no role here, right? So basically the state has an order, a ferromagnetic order, right? So basically these points, each point you lay in this line, okay? While if I sample my partition function at high temperature, we have this, so the points will be spread all over this 3D space, okay? So basically here you can even guess this intrinsic dimension, right? So here you have intrinsic dimension equal to 1. So we have the manifold of my partition function lays in a space with intrinsic dimension equal to 1, and here with intrinsic dimension equal to 3, right? So here is just to give you an intuition, right? Of course, you want to analyze many body systems, right? So the number of particles in my system will be super large. All right, so this is, so what I want to do, it's in some sense simple, right? So what I want to do is I want to analyze data sets that emerge in the vicinity of different kinds of phase transitions, okay? So here you consider classical transitions, transitions that happens due to the variation of the temperature. But if time allows me, I will also consider some quantum system, okay, so quantum phase transitions, okay, so transition that happens exactly at temperature equal to 0, okay, and is induced by an external parameter. And then you want to compute or to estimate the intrinsic dimension of these data sets and see how this intrinsic dimension change as a vary temperature or this external parameter. So this is what we did in these works and what I want to explain to you. So basically, this is, so is there any questions so far? Okay, so this is basically the outline of my,
can I ask a question?
Sure.
Are we talking about quantum phase transition, no?
Yeah, you talk about both about classical and quantum.
Yeah, because I'm trying to understand the meaning of configuration space in quantum physics.
Yeah. This I will explain later.
Okay.
For quantum system, is a bit tricky how you define data sets.
Okay.
So in fact, this is it's a bit tricky, but I will try to explain. I think time is you allow me. So defining quantum data sets is a bit tricky. So and I will try to explain later. I will explain later. All right. So then, the outline of my talk is the following. So first, I want to give you an overview, to be more specific about the kind of systems, physical systems that are interesting. Then I will mention some quantum systems, and also I want to do an overview of this field. Like we are not the first one to propose that. I mean by analyzing physical properties through data sets, like this data-driven approach that you are assuming. So I want to do an overview of the field, and then I want to discuss how we can estimate this intrinsic dimension, okay? And finally, I will show my results, okay? All right. So then let me give you like a feeling of the kind of system that I have in mind, okay? So, and the motivation, the kind of Hamiltonians that I study, like both classical and quantum, are motivated by these experiments, these recent experiments that people are doing. And basically, this experience is like a synthetic quantum system. So basically, so it's like, for example, optical lattice system. So you have like a bunch of atoms that are trapped in a lattice that are generated by lights, okay? And these systems are in a temperature that is super low. So basically, quantum effects plays a very important role. And also one important aspect of this system is that we are in a strong correlated regime. So basically the particles in these systems interact. The interaction between the parts is something that you have to treat. Like you cannot use mean field or like such kind of approximation. But another important aspect of this system is that you can realize phase of matter. Like, so you can really realize quantum Hamiltonians that like usually you don't know how to solve analytically or even numerically. So you can realize that in a tunable way. So then you really do a kind of simulation, your quantum simulation. You really can probe your system. You can solve certain kinds of Hamiltonians in the many-body physics. Okay? And then you can realize phase of matter, for example, like antiferromagnetic phase of matter. And also you can study phase transitions, for example, like phase transition between different magnetic states and so on. All right. Yeah. So this is the one aspect that I mentioned that this about the system. It's important is tunability, so you can really control the parameters of the system. So you can really do quantum simulations of quantum many-body Hamiltonians. Okay? And another important aspect of this system is how to probe the system, right? So then basically you have a quantum state, right? And then you want to probe the system, right? You want to see that you have an antiferromagnetic state, for example, or you have a Z2 state, a state with order Z2 or Z3, right? So then you have to measure something, right? So basically in this system, they are, you can probe local properties. You can measure like correlation functions, nearest neighbor, two-body correlation functions. Okay? But you can also measure more complicated things like quantum correlations, also like quantum properties like entanglement. Okay? Despite it's much more difficult to measure quantum entanglement. So I won't talk about this. So I just want to mention that indeed it's possible to measure quantum entanglement in this system. And the idea of measuring quantum entanglement is exactly what I want to do here, but in a different perspective, is really to characterize the system, right? So you have like, so certain phase of matter, you can use quantum entanglement to characterize certain phase of matter. So this is the motivation why they want to measure quantum entanglement. Okay? All right. So, but the one aspect about quantum entanglement is that it's super hard to scale the system size. Okay? So it's super hard to measure entanglement for a very large system size. Okay? And what another thing that they measure, that, as I mentioned, is local properties. Okay? So they can really measure wave function snapshots. Okay? So it's like you have your quantum state, you have, let's say, your wave function, and then you do a projective measurement. Okay, so then you have like a wave function snapshot. And then they can do this measurement like a certain number of times. And then at the end, they have a bunch of wave function snapshots. Okay? And with these, so this wave function snapshot, so it basically is a data set. You can see as a data set, right? So each image here, it's a row here in this data set, right? So basically with this, you can compute, for example, two-body correlation functions. Okay? So this is what you usually do in many-body physics, right? When you want to characterize, let's say, an antiferromagnetic state, you measure the correlation function, okay? And then you see if you have long-range order, for example, right? Of course, if you want to measure higher order correlations, can be a bit tricky, okay, but in principle you can measure. But what you want to do here is really one of the motivations of developing these.
Sorry, Tiago. I have a doubt here. When you say wave function snapshots, this is like it's like a picture of the wave function itself.
It's like a projective measurement, right? So you are really sample the terms of the wave function, right? So if you do a projective measurement, you can collapse.
Yeah, but in which basis? I mean, because
exactly. This is
because if quantum state tomographer 256 atoms, this is impossible.
Exactly, I totally agree. Yeah,
yeah, so, it's impossible.
So what they do, the basis is fundamental, right? So what they do, they choose a basis. So basically, usually they choose. So they in these experiments that I mentioned here, they try to simulate this quantumizing model, right?
Okay.
This quantumized Hamiltonian, right? So basically, they choose the SZ basis.
Okay.
And they just measure in the SZ basis. Of course, what they have at the end, the information that they have at the end, is much less than quantum state tomography, right? So it's
oh yeah.
And it's okay, but you can, for example, measure with these wave function with these snapshots in the SZ basis. They can measure correlation functions, like two-body correlation.
Oh, that's right? Nice.
And they can measure, for example, the order parameter, the SZ magnetization. Okay?
Yeah, that explains why it's a Nature paper.
Yeah, and so, but you're right. So, but if you want to measure entanglement, then you have to do something else.
Yeah,
yeah. Okay.
Okay. Thanks.
So then they do another thing that is more complicated. But it's still less complicated than the quantum state tomography, but it's much more complicated than these snapshots.
Okay, thanks.
Typically, they do like 1,000 measurements, more or less, like of the order of 1,000. So they have 1,000 snapshots, and then they can compute. So then they have these data sets, right? like exactly this 0 and 1. So 0 means like no occupation, and 1 means like spin up, for example, and 0 spin down, right? In this language of quantizing model. And then you can measure observables with this. But what you want to do, you want to analyze the data set as a whole, right? So we really want to do this, like really compute properties of the data set, okay? Like this intrinsic dimension. So in a sense, what to do is try to develop new tools to characterize quantum correlations based on this kind of data sets. All right. Okay, so yeah, so then it's this is the goal, right? Try to suppose that the experimentalist give me this file with this data set, and then I want to see if this data set is represents a state with ferromagnetic order, for example, topological order, so on. So how can you do this and write it? So these ideas of using like machine learning concepts and methods to achieve this goal was, I think it started more or less in 2017, 2016. And I think the first, so here you mentioned the first works in these directions. The first work, one of the first works in this direction was this work here, right? So the basic idea here is to use a neural network. Okay? So a neural network, basically it's these high dimensional functions that you can train, right, to perform some tasks. Okay? So basically here you can train this neural network with like easing snapshots. Like this is really Monte Carlo snapshots. Okay? So I do the simulation, and for each Monte Carlo configuration, it's a snapshot. And then I can train this neural network to identify if my phase is ferromagnetic or disorder. Okay? So then I train with a certain amount of data, and then if I want to feed with new data, then in principle, the machine will be able to distinguish the phase if the data that I'm feeding is ferro or disorder. Okay. I think this was the first work in this direction. And they use this, what it's called in machine learning, supervised approach. So they use it labeled data. Okay. So you really know, in this approach, you really have to know your phases a priori, right? Because you have to train a priori your neural network, and then use the trained neural network to distinguish phases. So another way to do characterization of phase of matter with data sets is using unsupervised approaches. Okay? And the unsupervised approach, the idea is to use unlabeled data. So the idea of the unsupervised is you want to see structures in your data set that allows you to, for example, characterize phase of matter. Okay? So here, the first work in this direction was this work of Leiwang in 2016. And they use this very simple method. This is called the principal component analysis. That is essentially a linear algebra. Okay? So the basic idea of this method is to do a dimension reduction. So basically, as I said in the beginning, your data set, your physical data set lives in a space that has a high dimension, like basically the dimension of this space is equal to the number of particles, right? But then you can project this data set in a space of lower dimension, like 2 dimensions more specifically, as shown here in this picture. And then what they saw, Leiwang saw, is that for the 2D Ising model, what they saw is that in the order phase, you have the formation of clusters in this in the order phase. Okay. Oops. And in the disorder phase, you don't have clusters. So this information can allow you to distinguish if you are order or disorder phases. Okay. Okay, so and after that, I think much more works appears in the literature, like using much more sophisticated approach and so on. All right, but I just wanted to mention these 2 works. And the idea here, what we want to do in a sense is use this unsupervised learning approach, right? So you really want to look at structures of the data set.
Tiago, I don't know if you know how to answer this question because it's a paper from other guys, but what's the physical interpretation of the formation of these clusters?
Yeah, it's related to the symmetry of the order parameter. Okay, so basically, so here you have 2 clusters. Right? So basically, what we have here is the following. So here, so basically the yellow configuration, the yellow points, right, are like configurations. Yellow and blue, no, sorry, yellow and red are configurations that are, yellow and blue, are configurations that are below the transition. So then your system is already ordered, like. So basically, the configurations in the right side means that the majority of the spins of these configurations are pointing up. Okay.
Oh, and that's why you see reduction in the dynamics. Okay, and the other one is it's disordered. So, but okay, okay, perfect.
So
perfect.
So there are like
it fits the other figure that you showed to us, the 2 cubes. Okay.
Yeah. So it's really it's really related to the symmetry of the order parameter.
Okay. Yeah.
So if you consider like the Q-state Potts model, that the order parameter has Zn symmetry, then you have the number of clusters that you have is related to this n of the order parameter. Right.
Okay, that's nice. Thank you.
Yeah. So it's really, you have really an interpretation, right? I think the nice thing about unsupervised approach is exactly that, because you can relate it to physics, right? Let's say, in a less black box way. All right. Yeah, but yeah, so one reason why you want to do this, right? I think, and I think the answer, here I will give one answer, right? So typically, it's not so easy to characterize phase of matter, right? So it's not even easy to, at certain phase of matter, it's not even easy to define an order parameter, right? So the order parameter can be extremely complicated. And okay, so the idea of this data-driven approach is that you don't need to have a lot of information about the system, right? So this is one motivation to push for this kind of approach. Okay. All right. And again, returning now to our approach. So the idea of our approach is that we want to do a kind of unsupervised learning without any kind of dimension reduction, right? So and here what you do is to really analyze this intrinsic dimension. Okay, so now let me return to the main character of this talk, that is this intrinsic dimension. And let me briefly explain how to estimate this intrinsic dimension. Okay? I think this is still an open problem in machine learning community, like how to estimate this intrinsic dimension. It's a hard problem, but here you use an approach, say an state-of-the-art approach to measure this intrinsic dimension that was developed by one of our collaborators. Okay? So the basic idea of this approach is that you can relate this intrinsic dimension that I gave the intuition in the beginning to distance in configurational space. Okay, so imagine that you have your data set of Monte Carlo configurations or exponential configurations, and these configurations are points in a high dimensional space. And then what you need to do is to compute distance between these points. Okay, and distance here, I mean like a metric. Of course, I have to define a metric, but here I use really conventional distance, like the Euclidean and Hamming distance. Okay. So, and then what's shown in this paper, 2017, is that you can relate this intrinsic dimension to the statistics of distance. Okay, so more specifically, the probability distribution associated to this quantity here, mu, that is basically the second and divided by the first distance of each point. So for each point, I compute the distance between the point and the first neighbor and the second neighbor. Okay, so then I have R2 and R1, and then I have this mu. Okay, and if I do this for all the points, I have this probability distribution function. Okay, and what these guys show in this paper is that this probability distribution is related to this intrinsic dimension. Okay. And one assumption, of course, I won't have time to explain in details how to arrive in this formula. But one of the assumptions of the method is that the data set is locally uniform in density. Okay. All right, so then you can apply this approach. Okay, so basically what you need to do is that giving a data set, you compute this distance, and then you can empirically measure this intrinsic dimension by doing a fit in this formula. Let me show some examples. So here,
Tiago, this result that you mentioned about this probability distribution, is this something like in random matrix theory, like you have a universal distribution about the ratio of the distance between next nearest neighbors, and if the system is chaotic, so this statistic is like Wigner-Dyson, and if it's integrable, so it's Poisson distribution. Is this something like this? Actually, the question is, where does it come from?
Where this formula come from? Yeah, yeah. So basically, so locally, if you look locally, if you draw balls around, so if around each point, so the deduction of this formula is purely, let's say, geometrical. So if you draw balls around each point, you can show that let's say the area of the circle it depends on the effective dimension of this data set. So basically, it scales with the radius of the circle that you draw around at this point, and with the dimension, the effective dimension of this data set. Okay, that is the intrinsic dimension. Okay, so so this is the starting point to deduce this formula. Okay, but it's a more geometrical approach to deduce. I don't see any connection with. Actually, I don't know. I don't know if there is any connection with this random matrix theory results. Okay, so I don't know this.
Okay, so, but let me see if I understood. You're saying that this probability distribution, it fits every kind of data you have. You know, what is this probability distribution? You know, that's what I'm trying to understand.
Yeah, I mean, your data, like for example, this data here. Let me, your data, I mean, of course, if the assumptions of the method are okay, this data set is locally uniform in density.
Excuse me, just I have a question about what do you actually mean by saying is locally uniform? Is it a smooth function, or just like every point sees the same vicinities or something like that? Yeah. What is it actually, please? Sorry.
Yeah, locally means in the scale of R1 and R2, this distance here, right? Because the method just depends on the first and the second nearest neighbor distance of each point. So basically your data set should be, so the density of points of the data set should be uniform, should be constant within this length scale, right? So this is one of the assumptions.
Okay, thank you.
Mm-hmm. Yeah, and answering the question of Pedro, I think the idea is that if your data set respect this assumption, in principle, of course you have to check that, right? So of course your data set, you exactly fit this formula, right? So here I show some examples. So here I show instead of showing the probability distribution, I show the cumulative distribution, just because it's easier to fit. So just I integrate this formula. So this is the cumulative distribution. And I fit the cumulative distribution of the data, right? That will be aligned, okay, with this formula, okay? And then I can get, from this fit, I can get the intrinsic dimension, okay? So here I show the two examples that we still have, we still know how is the intrinsic dimension, like, let's say, intuitively, you still know that in the line, right? So remember the example that I mentioned at the beginning. In the ferromagnetic case, the intrinsic dimension should be equal to 1, right? And in the infinite temperature case, the intrinsic dimension should be like essentially the number of sites, right? Equal to 3. So in this case, we can really show, like, first that your data sets, these empirical data sets, fits that formula, like really follows a line, and then from this line, you can compute the intrinsic dimension using this approach, okay? Of course, there are drawbacks of the method has some drawbacks. For example, if you consider like discrete data sets, like qubits, right, 0 and 1s, in principle, the method should not work because you violate this assumption of the data set is locally uniform. Yeah. But you can always check. You can always check if your data set really follows this probability distribution empirically. Okay, so this is what you did. Okay. All right, and also this is an estimation. Is a local. Let's say here is a bit more details of the method. This is a local feature of. So this the intrinsic dimension that I computed with this method that I call 2 nearest neighbor approach. Is a local feature of the configuration space, a local, so it's a local, I'm measuring locally the intrinsic dimension, right? Locally, I mean like within the scale of R1 and R2, these two distance. So, of course, you can have a very complicated data set that the intrinsic dimension in certain region of the data set is one value. And then if I go for another region, the intrinsic dimension is another value. In this case, the method you fail because I'm not assuming that. All right. Okay, so this is just to give you an intuition of this approach. Okay, so now I'm really planning to go to the results now. I don't know if there are more questions about the approach. Okay, so now what I do is really analyze data sets. I will start with classical systems, right? So basically I have my partition function, then my model, that is this energy. And now you consider different models, okay? So each model has describe a phase transition, like a second order, a first order, or even like a topological phase transition, this Berezinskii-Kosterlitz-Thouless transition. And I won't enter in the details of how I generate the data set, but the idea is that I use Monte Carlo simulations, okay? So like I use this Metropolis algorithm. Some case I use the Wolf algorithm. So basically I can generate these samples, right? I can do important sampling, okay? So I can generate a set of samples. So here I generate like 50,000 samples, okay, for different models. And then I can use this approach that I briefly explained before, this intrinsic dimension. All right, so basically then now come some results. Okay, so I will start with classical systems. So here is the two-dimensional Ising model. I guess you guys are aware of this model. So basically this model describes a second order phase transition, right? Between a symmetry broken phase and a paramagnetic phase. And the remarkable thing, the most remarkable thing about the critical point here is that we have like a correlation length. So basically your correlations has a length that diverge as you approach this DC, right? And then you can, with this, we can predict how physical quantities you behave, right, close to the transition. And then you can. Okay, so now let me show some results, okay? So of the intrinsic dimension, right? How the intrinsic dimension behaves as a function of temperature, okay? So here are some results for the 2D model. So one thing that we observe is that, like, for high temperature, basically the intrinsic dimension decrease as you start to decrease the temperature, okay? But then close the transition, you observe a minimum of the intrinsic dimension, okay? And then it increases again, right? So then it goes to a value that approach like 1, okay? So this is the behavior of the intrinsic dimension. So when you saw this result, we didn't understand like why is the case. But one thing that we notice, this is more empirical, but we notice that this minimum here shifts towards the critical point, okay, as we increase system size. Okay, and this is typical of size scaling, finite size scaling. Okay, so physical quantities also has this kind of behavior, right? So it has let's say a critical feature, close the transition that shifts toward the critical point. So then this motivates us to do a kind of finite size scaling of this quantity, okay? And with this finite, so here I show the finite size scaling that you did of numerical results. We show, so first of all, we study how this minimum shifts towards the critical point as a function of the size of the system. Okay. And here you did a data collapse. Okay. So with that, you can compute like both the critical temperature, but also the exponent, a critical exponent that is associated to this, to the divergence of the correlation length. Okay. And the results that we got from our numerics is that it matched with exact results, right? Within error bars, of course. Okay, so this really indicates to us that this quantity that is let's say a generic feature of the data set exhibit scaling behavior. Okay, so this is more empirical.
So excuse me once again. So just checking if my intuition is correct here. I would expect that for in the thermodynamic limit, we would have intrinsic dimension 1 or 2, because I mean in the critical point, because there the only scale is the correlation scale, right? Or isn't that right? Let's see if
I think your intuition is right? Because at the end, I mean, this intrinsic dimension, if you want, it measure like, let's say, in terms of words, measure like the number of degrees of freedom that you need to put to describe your data set, right? But the problem is that the way that you measure this intrinsic dimension is not so simple. So so first of all, it's a scale-dependent quantity. So it depends on this scale of that I mentioned at the beginning of that I mentioned before, like of R1 and R2, right? So it's not so simple. So the only case that we understand very well the actual value of intrinsic dimension is like for very low temperature in the order phase, like then you expect that it goes to 1, right? And in the infinite temperature regime, right, then you expect that the intrinsic dimension should scales with the number of sites, okay? So later on, I will try to draw an explanation why it should be a minimum at least, okay? And this is connected to the correlation function, like the intrinsic dimension is related to a correlation function. Yeah. All right, so yeah, so then what we did was we explored that, right? You look at all the kinds of transitions numerically. So the other transition that we looked at was this Berezinskii-Kosterlitz-Thouless transition that is a topological transition. So here, different from the Ising case, the classical Ising case, we don't have a break of symmetry, right? So you don't have an ordered phase with a local order parameter. but instead you have a critical phase, right? So basically in the left side here, the correlations are still critical, or still power law, right? So it's not long range. And in the transition here, it's a topological transition. So you cannot describe this transition with a local order parameter, right? But what turns out that the results that we observed that surprise us as well is we also have a similar behavior to what we saw in the Ising case. Okay, so we have this. So for a high temperature, as you start to decrease the temperature, the intrinsic dimension has this kind of minimum here, okay, that shifts towards the critical point as you increase the system size. Okay? And also you also can do a kind of data collapse, right? You can put all these points in a single curve, like. And this collapse, of course, you assume the right universality class of this transition. But if you assume the right universality class of this transition, we can. So here we also our results strongly indicate that this quantity also exhibits this scaling behavior, right? So it has a signature of the transition, right? But here is a bit different from the Ising case, because here the transition, it's the nature of the transition is completely different, right? So it's all right. Okay, yeah. So then we try to understand better, like why this generic feature of the data set exhibit this universal scaling behavior, okay, in these classical systems, okay. And our explanation is related to the fact that we also realize that distance in configuration space is related to correlation functions, to physical correlation functions. Okay, so just to explain that with more detail. So basically, so here is the definition of the Euclidean distance. So you can write the Euclidean distance between two configurations, okay, I and J, in this way. Okay, and this depends on this overlap here. Okay, so this is not a physical correlation function, okay? But what you observe is that so what we show with some assumptions is that this overlap here can be mapped in physical correlation functions, like correlation functions between sides of the lattice. Okay. So the basic idea is that this distance, so, and at the end, the intrinsic dimension is related to this distance, right? So these distance are related to correlation functions as physical observable, right? So, and as these correlations, of course, diverge and has this universal scaling behavior, like this reflects in this generic property of the data set, this intrinsic dimension. I won't show here in details, but we also show that numerically that you can spot the transition and also characterize the transitions with the distance. Okay, so just looking the distance in configuration space, we can use this distance to characterize the transition, these transitions. Okay. All right. Okay, so yeah, so this is was the classical part of our work, let's say, but you also try to generalize that for quantum phase transitions, right? Like transitions that happens at zero temperature. Okay, so in this case, the system is described by a Hamiltonian that is quantum, right? So basically, so the kind of system that you consider was quantum spin models. Right? And basically, the basic idea is that your Hamiltonian is an operator here, right? So you have the terms, you have two or more terms on the Hamiltonian that doesn't commute with each other, right? So this is the basic idea. And then the situation is much more complicated, right? I think this is related to the question that Lucas asked me in the beginning, how we define quantum data sets, right? So I think for the first thing that you have in mind, that you need to have in mind when you talk about quantum is that when you do measurements, somehow you have to define a basis, right? You have to, you cannot measure like, let's say, in our case here that we are dealing with a spin system, you cannot measure like the X and the Y component, right, at once, right? Or the Y and the Z component. So you always have this limitation. And here, the way that you define the quantum data sets is exactly what we do in quantum Monte Carlo simulations. Okay? So we map the partition function, the quantum partition function, in a classical, let's say, partition function. Okay? So you use this path integral mapping, right? So basically here we have the trace, right, of this operator here, and then you can divide this operator, right, in like, so delta tau here, it's like a function of beta, okay, and then we divide this operator in a product of operators, right, and then we introduce these bases here between each operator, right? So then you have like a path integral representation of the quantum partition function. Okay? So then basically, let me try to explain with a picture, right? So basically, let's suppose that you have a one-dimensional system, right? So then I have different, what we call time slice, right, of my partition function. Okay. So basically, you essentially map it the one-dimensional problem in a two-dimensional problem. So, and then for quantum cases, for the quantum problems that you consider, we consider two kinds of data sets. The first one was what you call a single slice data set. Okay, so basically the data set are formed by the first slide of the partition function. Right? And the other kind of data set that you consider is it's formed by multiple slices of the partition function. So you consider these two kinds of data sets. And then you play the same game, essentially the same game that I explained for the classical problem. So we compute the intrinsic dimension of these data sets. Okay. But again, we choose a basis here. So this each alpha here is like it's written in terms of SZ basis, right? So you have SZ1, SZ2, SZ for site 1, SZ for site 2, right? All right. And then here, yeah, again, I will show.
Yeah, sorry. Just to see if I understood. The last equation that you wrote is time ordered. Is that correct?
This one?
No, yeah, the in the bottom.
Mm-hmm.
Is this time ordered?
Yeah.
So what you are doing is just mapping spatial correlations into time correlations.
Imaginary time correlations, yeah.
Okay.
Imaginary time correlations, yeah, because
okay.
yeah, here, yeah, everything is like imaginary time, right? Because for it, yeah. Okay. So this is exactly how you can simulate this kind of system, right? So when you do quantum Monte Carlo, you do exactly that, right? So then you map the system in this like 2D, the one-dimensional system, let's say, in a 2D, let's say, cell, in this 2D cell, right? So each slice here is a configuration, right? Alpha 1.
Okay.
And then you can sample that, right? You can like you do for the class, you can flip a spin and then accept or not. The idea is that.
That's nice. Thanks.
Yeah. Mm-hmm. So yeah, of course, like when you consider, like when you have correlations in imaginary time, you also somehow get information about other directions, right? Because so we also, as you said, you also have correlations in imaginary time, right? There are certain quantities that depends on this correlation, right? All right. Yeah, and yeah, the interesting is also we can, in the quantum case, you define two kinds of data sets, like single slice and multiple slice. And then the results turns out that was similar to the ones that we got for the. So here is this quantumizing model, one-dimensional, that you can map in this 2D cell, right? And then you can sample this configuration, and then you can compute the intrinsic dimension. Okay? So here I show the intrinsic dimension as a function of H. So H is the transverse field of your Hamiltonian that induced the transition at temperature equal to 0. Okay? So here temperature is equal to 0. And what we saw is that so you also have this minimum of the intrinsic dimension, and this minimum shifts towards the critical point as you increase system size. Okay? So here you also compare with physical observables. So here's the susceptibility in the x direction. Okay? And the susceptibility in the x direction also has this kind of scaling, right? So you have this, so here the scaling is like the peak, right? And then the peak shifts towards the critical point. So you have this kind of, and the other case that you consider was the other model that you consider was this one-dimensional XXZ model. And this model is interesting because it has a BKT transition. It's this topological transition that I showed before for the classical case. And here you also have similar behavior for the intrinsic dimension. You have this minimum that seems to shift towards the critical point. Okay. And one interesting thing is that, so here I consider these multiple slice data sets. Okay. But if I consider in this case the single slice data set, I don't see any signature of the transition. Okay. While in the Ising case, sorry, I didn't put these results here, but I can mention, in the Ising case, I also, so here is also multiple slice, this multiple slice data set. But if I consider single slice data set, I still see a signature of the transition, but for the BKT, no. Okay? And I think the explanation is that the BKT, so you really need correlations in imaginary time to characterize the transition, because this transition is really a topological transition. So you cannot characterize this transition with just like local correlations. Okay? So local correlations, you just need single slice to compute, right? Because you can compute all the correlations in a same slice. Okay. So it really, really depends. All right, so I think this is what I wanted to tell you. Yeah, I think that the main message of these two works that we did was this, I think like generic features of dataset XBit scaling behavior in the vicinity of critical points, okay? And I think so our explanation is that the reason for that is that somehow these generic features like the intrinsic dimension and also this distance that I mentioned, it's related to correlations, okay? Correlation functions. We cannot spot yet like exactly which correlations, but from our results, I think this goes beyond the two-body correlations, okay? So this really, these quantities are really related to like many body correlations. Okay. For that reason, you are able to characterize like this BKT transition, for example, that is typically super hard to characterize. So you need like correlations that goes beyond like two-body correlation. Okay. So somehow we think that this kind of analysis that you analyze the data set as a whole, right? And so you really have the data set and then you really analyze like global properties of the data set. It's more rich than simply compute two-body correlation functions. Okay. All right, so this is what I wanted to tell you.
Okay, thank you very much, Tiago. Questions?
Check also YouTube, but I have plenty of questions actually. If anybody wants to talk something.
So we have no questions on YouTube yet.
Yeah, I have one thing that I don't quite understand. Let us think that I give you some data set and said, look, this is a data set. How do I choose the measure? How do I choose how to measure distances? Because I don't know the geometry of the manifold on which the data sets define it, and I don't know the geometry, even worse, I don't know the geometry of the submanifold of the intrinsic dimension. So how can I make sure that I'm choosing the correct distance? I mean, you use it the Euclidean distance, but it could be any other one. I mean, the manifold. Why is the manifold flat?
Yeah. So, yeah. In fact, this is something that you cannot. So the choice is more like based on physics, right? So basically, like configurations that are similar in energy, like for the classical case, at least you can use this intuition, like configurations that are like similar in energy, like it has, let's say, like the same difference in energy, let's say configuration 1 and configuration 2, the difference in energy between them should be like for example, the Potts model, right? You use the Hamming distance, right? Because in the Hamiltonian of the Potts model, we don't make difference between like configuration 1 and 2 and 2 and 3 or 2 and 4. Okay, so then you use the Hamming distance because the energy of between configuration 2 and 4 is the same between 1 and 0. Okay, so then you use the Hamming distance. But we cannot do we don't know if the data set is flat a priori. We don't know. This is
because I mean,
so the choice of distance is based on this intuition on physics.
Yeah, because I'm thinking about a single spin. I mean, if I have a single spin, and then the dynamic is very simple, but the configuration space of this guy, actually, this is the state space, and this is one thing that I'm trying to understand. The state space of these guys is a sphere, which is not flat at all.
Yeah, but here you always choose SZ, right? For the quantum case, right? You always have to choose, so you'd be like plus or minus 1, right?
So you have the configuration space is built up from the results of measurements.
Yeah.
Yeah, why is this flat? I don't understand.
But I think it should be, it can be not flat, right?
Of course, after
it's not flat actually. Like
assumptions against the experiment, but
yeah. So like let me give you another example. Like so here there is another thing. Also here you analyze it like both discrete data sets, like that data sets that is each coordinate is 0, 1 or minus 1, 1. But also you analyze a continuous data set, right? So for the XY, for example, the data set is continuous, right? So and for the XY, we choose the distance in such a way that, like, let's say if the angle, what's the example? The first example that I show, right? If the angle between the two configurations are 2 pi, okay? So actually we didn't use this, here is just for illustration, but you use the cosine and the sine of, so to incorporate this idea, right, that I was mentioned physically, that if the energy difference in energy, it's like 2 pi and 0, the difference in energy should be exact. So the distance should be 0, right, in this case. So the configuration that we used was cosine of θ1 and sine of θ1.
Okay.
So somehow we incorporate that. But this data set is not flat, right? So I cannot see why it should be flat. I think the answer for the question is that the choice of distance is motivated by this the energy at the end of the configurations. Okay? So
and it seems to me, especially in this example, it seems to me that the intrinsic dimension is linked with the information that you have about it. Because I mean,
like
if I have all these pins pointing to the same direction, then I have intrinsic dimension equal to 1. Yeah. But to describe this state, I just need 1 bit of information.
Yeah.
But to describe the other system, the right of it, like I need the logarithm of the number of atoms.
Yeah, exactly.
To describe this system.
Yeah.
So I need much more information in this case.
Yeah.
Now, this reminds me some relations between Lyapunov exponent and the higher measure in the space.
Yeah.
Okay, thanks.
Yeah, I think at the moment you are trying to let's say formalize better this connection between the intrinsic dimension, this distance, with physical quantities, more specifically with correlation functions. Okay? This connection with information, quantities related to information theory. So this is something, that we didn't think about.
It looks like information theory.
Yeah.
And you can measure correlations using, for instance, relative entropy, or actually can measure distances and dimensions and volumes and all of these things using relative entropy.
Yeah.
Or other informational quantities.
Yeah.
Any more questions? Okay, so I have a question. Would it be possible to predict, for example, the first critical time in a dynamical quantum phase transition using this method?
Mm-hmm. So yeah, so I think so. I think you can also, yeah. So yeah, this is one thing that I proposed to Marcus to never study. You never try this, but I think so. I think you, because for the dynamical quantum phase transition, you can always map in a partition function, right?
Yeah. So, can you please go to that slide? I think so. The time slices you use to map to the path integral. That one. Yeah. Yep. Thanks. Yeah, because when we have a dynamical quantum phase transition, we only have one alpha, but that one alpha you can slice it. Yeah, using, like, for example, the H basis, the Hamiltonian basis, the one that's being exponentiated. And then I think you would consider only one of those columns, right? Would be something like that.
As a data set, you mean?
Yeah, for the dynamical quantum phase transition, because here you have many the x-axis. Just remember me, what's the x-axis really? The x-axis here?
The real space axis.
So can you go back one slide, please? Yeah, because there we wouldn't have to sum over alpha naught, right?
Yeah.
And then, yeah, I think it is analogous. I don't see why not.
Yeah, I agree. Yeah. Yeah, I think for a quantum system, like, the definition of the data set is always something that you should, and also, like, the intrinsic dimension, certainly it's a basis dependent for quantum system, right? So a basis dependent quantity. So if I choose another basis, depending on the system, more certainly you have different results. Okay? So the question is, so the still open question for me is if it's this, like, the behavior close to the transition, like this minimum is independent of the basis. So this question still didn't address it, but for quantum system, the intrinsic dimension is certainly dependent, basis dependent.
Yeah, I mean, this is linked with the information that you have, because if you change the basis of measurements, you change the amount of information that you get.
I need to enter the question if this is somehow related to some kind of more genuine quantum correlations. So this is still open questions as well. Yeah.
Yeah. Any more questions? Oh, let me see the YouTube. Yeah, no questions on YouTube yet.
Yeah, Petro should definitely explore the random matrix theory behind that, because it's ought to be related. It has to be. I mean, probably is. I would be really surprised if it wasn't. And I think he is onto something here. It's really nice to look at such data sets that way.
Yeah, random matrix theory is full of universal things like the probability distributions, and I mentioned the random matrix theory because it came to my mind when you showed that distribution probability, but I still don't know how random matrix theory should be related to the whole context and everything else.
Yeah, but because if he could map these problems to one of the canonical ensembles in random matrix theory, it would be, I think, would be really easy to prove that the intrinsic dimension is or is not universal in a basis. When we talk about the chosen basis near the critical point, because then like say if we have a Hermitian ensemble, all unitary transformations are invariant. So here we are. It's not basis dependent anymore, and it would be nice to show that something like that.
Yeah, that's true.
Yeah, I will think more about it. Yeah. The question is, what should we consider as random here? And what is the best ensemble to describe it? This is one of the major questions in random matrix theory. So, but I will think about it and get in touch if I thinking something interesting.
Sounds interesting, yeah, but yeah, to be honest, it's not my expertise. For that reason, I could not answer your question, but sounds interesting. I think these lines, yeah.
Okay, questions?
Yeah, just one more. I think one of the hotspots here is the use to spot the topological phase transitions, because you clearly have some signatures there. Does it hint to some topological order parameter or something like that? Can you elaborate on it, please?
Yeah. So I think so. As I said, my explanation for is that this intrinsic dimension somehow is related to many body correlations, like that goes beyond two body correlation functions. So for that reason, we have signatures of the transition. Okay? But the topological phase itself is more complicated. So I still don't know, and I think not that we cannot use this intrinsic dimension as a topological invariant, for example, to characterize the phase itself, right? So I think it's more like, because in the transition, you expect that some correlation, right, that goes beyond two body correlations, for example, even a topological transition should have a singular behavior, right? Should diverge somehow, right? So this is what you see for the Kitaev model, for example, right? One-dimensional Kitaev model. You have these string operators, that string order parameters. These string operators diverge, so this correlation diverge. So I think the reason that why you have a signature for the transition in the Berezinskii-Kosterlitz-Thouless transition is that, right? Somehow this intrinsic dimension is related to this correlation. But to claim that you can use the intrinsic dimension as a topological invariant, this is another story that we don't know yet. Okay? So I still think that we have to explore more. Don't know if I answered your question.
Okay, thank you. Yeah, you did.
Yeah. Questions? Okay, no more questions. So let me thank you again, Tiago. So thank you very much for the acceptance of the invitation. The talk was quite interesting. So thank you very much. And so that's it.
Thank you very much.
So,
yeah, thanks for the opportunity and also for the questions. I think it was a nice discussion with you.
Yeah, it was good. It was really good. So thank you, Tiago. And so we meet again, and we meet in 2 weeks. So thank you very much.
All right, guys. Yeah.
See you. Bye-bye.
Have a good day.
Yeah, you too. Thank you.